Yes.
Okay. Okay. So good morning, everyone. My name is Piotr Magierski, and I will give a talk on some results coming from Quantum Monte Carlo concerning properties of the unitary Fermi gas, which is apparently quite an interesting system. And this is something that we've been doing for the last couple of years. And these are the main collaborators, Aurel, who is also here, Joaquin, Kenny Roach, who actually helped us with the computational issues, and Gabriel Wlazłowski, who is my former PhD student and now is a postdoc here. So the Monte Carlo method, which we are using, actually is pretty standard. So I will shortly tell you what are the I will shortly mention some technicalities, but we'll mainly concentrate on the results which we obtained, and this will cover the equation of states and some relatively new results on the pairing gap, spin susceptibility, conductivity, diffusion, and maybe I will cover also the viscosity, which is kind of interesting quantity for the unitary Fermi gas. So for those of you who are not familiar with the term unitary Fermi gas, so just I will briefly remind you that we are interested in such a gas of fermions which interacts, which is dilute in the sense that the scattering length is the only parameter which governs the interaction between fermions, and the scattering length goes to infinity, and at the same time the effective range, or the range of interaction, is quite small, so you can say it goes to zero. So the range of interaction goes to zero, scattering length goes to infinity, and this is a system which is dilute. Still it is strongly interacting and non-perturbative. And what is nice about the system is that this is universal. For example, if you ask the question about the energy of this system as a function of temperature, so X is here the relative temperature to the Fermi energy, so this energy as a function of temperature will be some function, dimensionless function of dimensionless quantity X multiplied by the energy of the non-interacting Fermi gas. So it's interesting, for example, to find this function, and especially the value at zero temperature. And there are some experimental estimates what this quantity should be at zero temperature. This is about 0.37. This system is realized usually as a gas of atoms, like lithium-6 atoms that are trapped and cool down, and people can measure. And due to the so-called Feshbach resonance, one can reach for such an atomic system this limit when scattering goes to infinity and the range of interaction goes to zero. So in that sense, it's an interesting system, and it's a good, nice playground for non-perturbative methods like, for example, Quantum Monte Carlo. Another interesting feature of this system is that at low temperature, this is a Fermi system. At low temperature, it's superfluid, and if one calculates the pairing gap for such a system, and it turns out this pairing gap is huge in in comparison to Fermi energy. So for a system in a unitary, for the unitary Fermi gas, the gap, the pairing gap, is of the order, it's about half of the Fermi energy. So this is the largest gap in the superconducting system that we know. So even the high temperature superconductors that are, some of them are listed here, have a smaller pairing gap in comparison to the Fermi energy. So in that sense, it is the system with the largest pairing gap in nature that we know. So it also means that the standard theory of superconductivity fails in this case. So this is actually seen in this plot, because if you, here you have a pairing gap, and here you have a ratio of pairing gap to the critical temperature. So the BCS theory, the theory of superconductivity, gives you this value of the ratio of pairing gap to the critical temperature, and this is clearly violated for the unitary Fermi gas, and also is violated for high temperature superconductors. So, so that's in that sense, is also, this system resembles some similarities to the high temperature superconductors. So this is the motivation why this system is interesting to study. So, and let me say a few words about our approach. So this is the standard path integral Monte Carlo at finite temperature. So the Hamiltonian is pretty simple, contains the kinetic energy and an interaction term, where this coupling constant G is adjusted in such a way to have a scattering length going to infinity. So we place some fermions on the lattice. We work in the grand canonical ensemble, so we put everything in the fixed temperature at fixed chemical potential. We have a non-polarized system, which is good because otherwise we would have a sign problem. So we have the same amount of spin up and spin down fermions. We put them on the lattice, and we impose periodic boundary conditions. And we do standard Monte Carlo. So for example, if we would like to calculate the energy, we sample this sigma field, which is the auxiliary field that is introduced here, and this measure is always positively defined because of because we have the same amount of spin up and spin down fermions. So the coupling constant G, which we used, is related to the scattering length. So the scattering length goes to infinity. So this term cancels, this term goes to 0. So this is the only term which is still there, and this is the momentum cutoff, which is defined by the lattice constant. So there is nothing particular about this method. So this is a standard, rather standard approach. Mm-hmm.
I mean, it's not generally true that if you have an equal number of up and down electrons, that there's no sign problem, right? So what's particular to what you're doing which makes that true?
Oh well, if you calculate this, this action, so this action is related to this trace of this operator U, which is given here, and for the spin symmetric system, this is a square of this determinant. So you can see easily that.
This determinant is a real number, otherwise.
Oh, it's real number. So it's a real number. Yeah, of course. Yeah. Interaction is attractive. Oh, yeah, of course. Yeah, I should mention that. Interaction is attractive. Yeah. Otherwise, we wouldn't have a superfluidity in this system. Of course. Okay, so a few technical details concerning the simulations. So at the moment we can go to lattices of the order of 14 cubed practically. Concerning temperatures, we can reach the temperature relative to the Fermi energy of the order of 0.06 and go down to the densities of the order of 0.03.
How many particles you typically do in a collection?
So of the order of 100 to hundreds for these lattices.
And do you reach convergence for this size lattice? I mean, at the end you expect the lattice size to go to 0. The spacing could be very small, right?
Yeah, well, spacing is everything
So
is
the point that energy-
everything is defined in the units defined by the spacing. So the spacing, the lattice spacing is 1, and
Okay,
everything
so
is
the
related.
number-
Yeah.
So the number of lattices.
Yeah. So it means we should go with this quantity to infinity. Yes. That's.
Right. So have you tested the convergence of different observables function of the lattice size? Have you?
Yeah. Well, I will show the results. We always do calculations for many sizes of the box. So one comment here. So the limitation of the size of the box is not related to memory or something like this. It's related to the correlation length. So simply, we can do calculations for like 30 cubed, but then we would wait forever actually to get another uncorrelated sample. So this is the practical limitation.
How do you measure whether your samples are correlated or uncorrelated?
Hmm?
How do you measure whether they're correlated or uncorrelated?
Oh, like usual, we calculate the correlation function.
Correlation function of,
Yeah.
of what?
Oh, like for example, if we sample the energy.
And does that mean there are different observables that you could use?
Or the
that
correlation or the energy.
some decorrelate much faster than others.
So we mainly use energy as an indication for the correlation length.
There was another
Yeah.
question.
Yeah.
Yeah, the thing is that I was just thinking that I would think that if you would, the thing is that if I understand this right, to do sort of local updates, right?
Mhm.
So the thing is that if you would use, for example, the hybrid Monte Carlo, and you would find that the autocorrelation is really not a function of the volume of the lattice, right? It comes from the fact that you have,
Yeah. Well,
that the number of the sites increases.
Uh-huh.
as
yeah.
you
Well,
go
the
down.
hybrid Monte Carlo would be nice to apply here, but I don't know how to do that. I will shortly present the results of Joaquin and you and
Yeah, that's why I was
myself.
asking that, there has to
But
be
this is slightly different code, which uses this hybrid.
You haven't used that yet.
Yeah. This is because here we use this discrete sigma field,
Okay,
and
okay,
in
then
that
it
case
works,
it's
right.
difficult. At least I don't know how to introduce this hybrid
I think it is sort of like
Monte
it's
Carlo
it
in the
requires
case of.
like a continuous
Yeah,
auxiliary field, so then you need
yeah.
to switch to that.
Yeah.
You like to use that.
Yeah. So this is
Same scheme.
yeah. So this is not this code I'm talking about is not a hybrid. It's just
Alright, I see.
it's
It's
just
hybrid.
we change this sigma field in such a way to get an acceptance rate of the order of 1/2, and it's for the very large lattices it will give the very long correlation, very large correlation length. So that's the limitation. And okay, so we usually so for example, for the lattice like 10 cubed around the critical temperature, the correlation length is about 200. So we need to do 200 steps to get uncorrelated sample. And we usually take like of the order of 10,000 uncorrelated samples. So it means that the statistical error here is about 1%. But this is not statistical error is not the main issue here. Actually, the other errors associated to, for example, the fact that we have a finite lattice constant, so it gives some contribution from the effective range, and of course finite size effects. The fact that we have also the fact that this coupling constant is adjusted to 2 fermions with the center of mass motion equal to 0. And of course, if we put fermions in a box, we have fermions moving, and we can find 2 fermions with a non-zero center of mass motion. So that means we have some error associated with the fact that we use only one coupling constant to describe the whole system. But these errors do not exceed like 10–15%. That's our estimate.
So discretization of the time step, have you studied the
Sorry?
discretization of the time step?
Oh yeah, that we studied, and how many time steps we use. It depends. It depends, of course, on the temperature and density. Yeah, but this is not the. This is not.
Below the other errors.
Yeah, this is below other errors. So. Okay, so these are our rather old results concerning the equation of state for the unitary Fermi gas. And this is actually the pressure, but you can easily translate the pressure to the energy. This is something, this is related to the temperature. And this is comparison with the experimental results, which are actually black dots. So the low temperature limit is here. High temperature limit is here. So you see also some comparison with the virial expansion. And so at this point we had rather nice agreement with the experiment. So we were pretty happy, although there are some discrepancies, but you see that both experiment and the theory actually is, the data points are pretty scattered, so it's difficult to say what are the errors, what are the differences between the experiment and theory. But recently, there were some very precise experiments on the equation of state. These are this is the energy as a function of temperature, and the experiment are this red dots. This is the same, but here we have instead the density as a function of chemical potential at temperature. So we can well translate easily this figure into this. So in this case, we use this hybrid Monte Carlo, so this code that was written by Joaquin, and you also probably contributed. So, and this shows.
More than probably, we did the work together.
Oh yeah. Sorry. That's, yeah. So, so you two developed this code, and you can see that. Yeah. So you can see the rather nice agreement, except for the low temperatures actually. And the low temperatures, which are shown here. So this part actually, and this part here. So you see some discrepancy between the experiment and theory, and yeah, well, so these are calculations for various lattice sizes, and you don't see actually much improvement.
So experiments do not seem to agree themselves. So
Hmm?
experiments do not seem to agree much themselves.
Uh,
Are the black dots experiments too?
No. Black dots are some other Monte Carlo results. So these, yeah. So this hybrid Monte Carlo are these three types of yeah. So actually, our earlier results that I showed on the previous transparency, these are this white. Okay. So you see, they even at the previous transparency they agreed quite nicely. So now you see that they were slightly off actually.
Sure. So you have the calculation of Burovsky, and when how that's the same group, right? It's the
Yes.
Yeah.
calculation.
Yeah.
So
Yeah.
they are not. So which one are the Burovsky? Are they lower?
I think it's the one which is there on the far
right.
right. You know.
This one. Yeah.
That's the
Yeah.
old
This is the old one. This is This is the old yeah.
Wait, so what are these opens? Well, the line, the lowest line. What is
This one.
The old result.
Oh, these are our old results.
Your order.
Yes. So these results that I showed here actually.
Okay.
So these were.
So now the Monte Carlo calculation of you and the Amos group, they agree with each other?
Yeah. Well, you can see. So this is actually this I think is the they are coming from this Amherst group, if I correctly remember. Yeah. So and they yeah. So
The blue, which one are your calculations?
these three types. So yeah, and the black are the Amherst group. So they go here. So they cannot go to they cannot go below the critical temperature. So.
Do you have a plot showing the energy as a function of n, the number of lattice points? Because it's hard to see on this graph. I mean, you have convergence.
Energy as a function of number of particles. Yeah. We have somewhere probably. I don't have such a slide.
So these plots are all essentially, the various lattice sizes are essentially all at the same density, and there's no much variation really. Maybe a little bit up, a little bit down. So it's essentially converged there. But we don't have really the zero density limit. That really needs to be done.
So what was the reason for the previous disagreement? I mean, why are these numbers changing as a function of time with these methods?
Well, first of all, it was a rather small lattice, and we have a rather large density. So I believe this is the finite size effects that are responsible here. So these results are for 8 cubed, and the density is rather large. So and the large density means we have large errors coming from, for example, the finite effective range. And so we usually try to go to as low densities as we can, but of course that means longer times.
But it's not completely. I mean, the result with the Amos group, if I compare with your result, I mean, there are some discrepancies. I mean, if I look, it's hard for me to see, but I mean, if I look at the intermediate, around 1 temperature,
Yeah, I mean here.
I mean, they're not large.
Amherst is presumably at the infinite thermodynamic limit, so maybe you're seeing some
No.
But the thing which I sort of wanted to point out is that if you sort of kind of look at the lowest temperature that they have in the Amherst data, it sort of looks like it's going like in the same way like a Savo calculation. It's not where the movement is going, but the referee told me that I cannot put the statement in the paper, so you won't find it there. I mean, when we wrote the paper, this was
yeah, it looks like they deviate, but
well, the central values do follow the trend of our data, and the experiment is going the other way.
Yeah, but on the other hand, they say there's a large error bar here. Actually, you may not see here, so they can say always that this is still within the error bars.
Yeah, but I think there's a definite trend that it's sort of
yeah, well, yeah.
More than we keep current.
I also think so, but well.
That remains to be refined.
Is there any representative of the Amherst group on this in the audience that can comment on this? Oh. Yeah, so this is current status of the equation of state for this unitary Fermi gas. So another thing that we were interested in is the behavior of the pairing gap as a function of temperature. So as I told you, the fact that the ratio of the pairing up at 0 temperature to the critical temperature is of the order of 3, which is much larger than what is like twice larger than what the BCS theory predicts, gives us poses some interesting questions. How the system behaves close to the critical temperature. Because, for example, as we know from high temperature superconductors, there is this interesting phenomenon which is called the pseudogap phase, which some people attribute to the fact that there is a preformation of Cooper pairs above the critical temperature. So in BCS theory, the Cooper pairs form and condense at the same temperature. So we have at the same temperature we have a phase transition to the correlated system and superfluid at the same time. And it need not to be the case. You can have a Cooper formation and Cooper pair condensation at 2 different temperatures, and this temperature range between this condensation and formation is sometimes called pseudogap. So this is, for example, issue that we wanted to address, whether such an effect also appears in a unitary Fermi gas. Oh yeah, I will actually in the next slide I will address this question. So how we calculate the pairing gap? So we calculate the temperature Green function, and then we use this equation to extract the spectral weight function. And the spectral weight function essentially gives you the probability of the particle occupying the state with energy omega and momentum p. So it gives you information about the pairing gap. So this is not an easy task, because in practice, as we know, this value only for a finite number of tau, which is the imaginary time. And so inverting this this equation is not an easy task. It's we do it in the following way. So let me spend a few slides on some technical issues how we do that. So we have the following problem. So from Monte Carlo we get these values, the discrete set of these values, which are affected by statistical errors. And we know this kernel. This is the usually analytic function. And we would like to obtain this value, which in this case is the spectral weight function. So the problem is that these quantities are affected by noise. So actually there are a lot of solutions that are possible that fulfill this equation if we have G that we know with some statistical errors. So we use the so-called maximum entropy method. So we associate with this space some probability distribution. So we associated with the space some probability distribution that the true value of A is A under condition that we know the data coming from Monte Carlo. And this quantity can be rewritten using the bias theorem. So we have here the probability of having the data G under the condition that the true value is G, and we have some a priori probability that the solution is A. So this is the probability that is related to the entropy. And so this term in practice, so it's because this data coming from Monte Carlo are assumed to be distributed according to the Gaussian distribution. So this term is an exponent of this term. And this term, which is kind of a priori information about the spectral wave function, is written in such a form that we have here a certain model that we expect that our spectral wave function should fulfill. So this model is, the guess of this model is coming from some constraints on the spectral wave function that we know that the spectral wave function should fulfill. So for example, in that case, we know that this has to be spectral wave function should be integrated to 1, and also we know that this integral should give occupation probability. So the problem here is the following. So here we have a parameter which is alpha, which actually governs which term is more important. If alpha is too large, that means that our solution will be very similar to the model. So we impose some model and we get actually the solution that is very similar. So we don't want this. So we would like to have alpha which is not very large, but at some point, if alpha is too small, then the minimization of this quantity is numerically unstable. So you can see it here, for example. So this is let's assume the spectral wave function is this red curve. So it has, for example, 2 maxima, and assume we know it. So our model is very similar. So if alpha is very large, so we get a nice agreement because our result will essentially will be similar to the model. When we try to decrease alpha, so at some point you see there are some strange structures that appear, and it usually happens suddenly. So everything works nice until alpha goes below some critical value. So what we do? So in this case, it's like 2 Gaussians, two Gaussians, yes. So in this case, so we do something.
I thought when you do the maximal entropy method for response function, or you want to invert the Laplace transform, which is a little bit similar to this.
Mm-hmm.
Usually, when you have only 1 peak in the function, the maximum entropy works very well. But when you have 2 peaks, it might have trouble. But I guess you could.
Yeah. So we have.
It already has 2 peaks, so it's maybe.
Yeah, but we actually allow for both structures. So what we do is something.
Do you have a plot that compares the actual to the model?
Yeah. So this is the artificial. So this is actually the artificial. So we know. We assume some spectral. So this is just a test example. So we assume some spectral wave function.
I understand. But
Yeah.
for the model, did you take the same, or did you take something?
Oh, something similar, just 2 Gaussians.
You don't have a plot that compares them.
On the next slide. So we do something more complicated. So we assume a whole class of models that are parameterized with certain parameters. So for example, we can take a set of 2 Gaussians where the parameters are the width of these 2 Gaussians, the separation, and the height of the peaks, or something like this. So and then we adjust our model to find the best possible model in such a self-consistent procedure that we first solve our maximum entropy method using fixed model, and then having this solution, we calculate the overlap with what we got with the set of models, and we maximize this quantity. We define a new model within our class that we use again to solve the maximum entropy. And we proceed until we get self-consistency, so in the sense that our solution will not change during the iteration with some precision. And this turned out to be a very stable method, and it turned out to be pretty insensitive to what is your initial model that you start with. So, for example, if you look at the left panel, so this again, the red curve is the original spectral weight function that we would like to reproduce, and our model are two Gaussians with two Gaussians that can have various widths, various separations, various heights, and we start with a something very bad. So we start. This is our initial model. So these are two Gaussians; they overlap. Okay, and after the self-consistent procedure, we got actually very nice agreement, even that we started with something very wrong. So and the final model after final model, oh, it's somewhere here. Yeah, I probably don't. Yeah, so final model after many iterations adjusted actually to reproduce as best as it can the structure of the spectral weight function. So of course it depends very much on what class of models you admit, but once you have a good class of models, it doesn't matter actually from which model you start. You get something as close as possible to the exact solution, which is nice.
So what if you had started with 3 Gaussians? I mean, it can recover it in principle by making one of them 0, but will it do that? Yeah, with
3 Gaussians, yeah, that's an interesting question. Probably you either would have 2 Gaussian just overlapping, or one will disappear if this is possible.
But will it actually do that, or will it give you a third peak?
No. It won't. That we checked. In this case, it won't happen.
I mean, when you didn't do this, you were getting multiple peaks, right? So if you just say your model is 3 Gaussians, why wouldn't you get an extra?
It can happen. It would happen. It can happen if you put your alpha too small. Yeah, that's true. So for example, in this case, if you have a wrong model and you put your alpha too small, that you can have something really strange. Probably that's true. Yeah.
But even if I have a large alpha, I mean, the alpha is only preventing deviations from the model, and so the 3 peaks are consistent with the model. So why would you not get 3 peaks?
We tried different. We tried the different options, but unless your model is very incompatible with exact results, then otherwise we never get such a strange behavior like a third peak or something like this.
Okay, have you tested this method in a case where you know what is the exact solution?
Hmm?
Have you tested this method in a case where you can actually calculate the exact solution.
No,
Well,
no,
this is exactly.
Or this is a model which
This is exactly. This is exactly. So this is yeah. So
Yeah,
this,
but here he's starting with a
Yeah.
2-peak model. I mean, I'd like to see the same plot done with a 3-peak model.
yeah. I believe we did it. But I didn't.
But the
Well,
entropy
no.
term could still
Yeah,
be
yeah.
small if you have.
Yeah.
Yeah, it
So
could
from
be
a model
small.
which is 3 peaks and you
It can
you
recover
Mm.
it, but if it's smart enough to recover it, can recover it in 2 ways, by either by making amplitude 0 or by making it
Well,
coincident.
when you yeah, of course, when you construct your models, you need to have some physics inputs. I mean, it's you expect your spectral weight function to either have 2 peaks or 1 peak. It's very difficult to think about physical situation that you can have a spectral weight function with 3 peaks. I don't know what. But of course, in the case of quantities that you completely have no clue how it can behave, well, that could be possible. But in this case, I mean, we have rather good knowledge of how the spectral weight function behave in various physical systems. So it's either like 2 peaks that we have a gap, or we have just 1 peak. It can be broader, or because of the interaction, or sharper if you have a weaker interaction. But yeah, well, otherwise it's always kind of cooking. I mean.
Principle in superfluid liquid helium, you have n peaks in the sense they are getting smaller and smaller, so that, but they are there. So you
Yeah.
have the main phonon, the 2 phonons, 3 phonons.
Well, so it's always like a kind of a cooking procedure. I mean, it's you need to give some a priori information. Yes, so that's you cannot neglect this point. Yeah, that's.
You know the symmetry of the pairing state, true or false?
What do you mean symmetry of the?
If you were to, it has a particular form like K minus. I mean, it's the same pairing object as the BCS pairing object. I mean, when you say, what do you mean when you say pairing gap?
Well, the pairing. What I mean, I mean exactly the distance between 2 peaks of the spectral weight function at the Fermi energy. So.
But you're also associating it with an idea of superfluidity and
Yeah.
in the BCS context.
Yes.
Just by looking. It's just by looking.
Yeah. So it.
But does that say you don't know what that excited state looks like? I mean, if you were to think, could you write down a function that has, that's what I mean by symmetry. When I talk about the pairing function BCS, I can write it down. Right?
Yeah, but this is the BCS assumption. Yeah. Well, I'm not sure we know exactly. So what we can calculate here is a pairing gap. So this pairing gap here, it need not to be associated with the superfluidity, because the superfluidity we rather look. Yeah, it's just a gap. It's just a gap in the single particle spectrum. Superfluidity is related to the long-range order, so which is something different. So actually, the difference between the looking at the long-range order and the gap can tell us something whether we can have a gap without superfluidity, and this is what we would like to address exactly.
So you define the gap to be the distance between the 2 peaks.
Yes.
I remember in your paper.
It's actually it's twice the gap.
Twice the gap, yeah. But in the paper, I remember you also fitted a BCS like quasi-particle.
Yes, I will show it. Yes, yes.
But we don't really know if the BCS.
Yeah, but we can fit and see how good it.
So the delta you get from this fit is different from this distance between.
No, it's pretty. Actually, it's. I will show it. It's pretty similar. Yeah.
The reason I'm asking about the symmetry is because if you put that symmetry into the kernel or into the correlation function that you're trying to pull the spectra out of, then you can eliminate things that do not have that symmetry from the spectra. And this is I mean, it goes by various names with Poitzy or projection operator magnitude times spectral evolution type thing. And so you can basically plug in an object that has the symmetry you think that the pairing function has, and then you'll only get in your spectra things that have resonances with that frequency. And naively, I've never understood why people don't just try that in this kind of context.
Yeah, we didn't try it, but maybe that's an interesting thing. Yeah,
Maybe it's not
yeah,
so
yeah,
naive.
yeah.
Okay.
Okay, so this is these are the results coming from this maximum entropy, and this is the spectral wave function that the unitary regime. So the scattering length goes to infinity. So at the on this axis you have energy. Actually, it's all the frequency relative to the chemical potential, which is somewhere here at 0, and here you have a momentum square. So the gap is actually the gap is actually what you see here. So you have no states here. So this is at relatively low temperature. Then you increase temperature actually. So you increase temperature, and these two branches start to merge. And at some point above the critical temperature, the gap vanishes, and you have one branch. So the width of this is related to the interaction. So in the limit of non-interacting gas, you will simply have just a straight line, and this is what we call the gap. And okay, so this is and this is again, and this is what you asked actually. This is the fit. This is the system which is not exactly at the unitary regime. This is slightly on the BEC side, so the scattering length is positive. So it actually can have a larger gap, and we can fit actually the maxima of the spectral wave function to the curve, which we parameterize in the same way as in the BCS theory, the quasi-particle energies, and from that we can extract. Okay, so this is this is better visible here. So these white curves that I showed you here are actually coming from this formula, which is coming from BCS theory. So it contains a gap, which is the gap from the BCS theory, and we can also adjust the mass, effective mass, and we can also adjust. We can have some energy, some interaction energy, which is U, and this adjustment, it shows that it really nicely agrees with this BCS theory. It indicates that the effective mass is actually close to 1, so nothing changes. So the U, which in BCS theory have a meaning of mean field potential, is of the order of half of the Fermi energy. And of course, we can also adjust. We can also extract the gap. The gap will be actually this, the distance here. Okay. So so that's kind of surprising that this.
But BCS theory should not work in this.
Yeah, yeah. Well, yeah, that's interesting. The quasi-particle spectrum somehow looks similar, although critical temperature is completely different. So in that sense, it's yeah, interesting. Yeah. So what are the results of this analysis of this spectral wave function? So we look. So again, this is kind of a plot showing how the properties of the system changes as a function of the scattering length. So this is the unitary regime is here. This is the inverse of the scattering length. So the BCS systems, that means that they are properly described by the BCS theory, are here, and the Bose-Einstein condensates are here. So the critical temperature, so the temperature for the phase transition from superfluid to normal systems, behave somewhat like this. So it goes to the constant value on the BEC side, and and then the question is whether there are, above the critical temperature, there are these preformed fermion pairs. So that means if these preformed fermion pairs appear, that we would have a gap in the single particle spectrum, although the long-range order will be lost. So we'll have pairs, but without superfluidity. And so this is kind of a summary of our calculations, not only for unitary regime, but slightly off also for the BCS and BC side. And this is the comparison of the two temperatures. The temperature when the condensate fraction goes to 0, so the critical temperature, and the temperature where the gap in the single particle spectrum disappears. So these are simply uncertainties of the determination of these two quantities. So we can see that these two temperatures somehow merge on the BCS side as we expect, but they become different as we go to BC side. And apparently, in the unitary regime, there is a region where we have a system that can have a gap, but not being in a superfluid state. So, so that's our Monte Carlo. So these are the results coming from Monte Carlo. So what is the experimental status of this pseudo gap in the unitary Fermi gas? So in experiment, they can the measurement of the gap is difficult. So what they can do, they can excite atoms from the state that atoms interact strongly to the other states that they do not interact or interact weakly, and measure the energy and momentum distribution there. So from this energy and momentum distribution, they can deduce whether the system is in admits the pseudo gap regime or not. And what we can do, we can compare what they measured with our Monte Carlo results. Well, the problem with the experiment is that they do experiments for the system in a trap. In a trap, you have various densities. So in a trap, you can have at certain temperature, you can have actually a system that can be partly in a normal state at the edges, partly in the superfluid state in the middle, and possibly there will be some part of the system which is in the pseudo gap regime. But still, we can compare the quantity, what they call the energy distribution curve, which is essentially the quantity which is related very closely to the spectral weight function, but for the system in trap, which tells you what momenta actually are occupied by the particles at some energies. So these are the black dots. Blue dots are the experimental results, and the red curve are the results extracted from Monte Carlo. So they are extracted from Monte Carlo using the local density approximation. So because we have to transform our Monte Carlo that is performed for a uniform system to the system in trap. So we have to do the intermediate step. So we have to do the local density approximation for the system in a trap, and in this case, this function phi as a function of temperature is coming from Monte Carlo. So as you can see, the agreement is quite nice, although it is also criticized by other groups, because other groups are also measure the pseudo gap using different techniques, and they do not see pseudo gap. So
are those also Monte Carlo, or are those also Monte Carlo? Or
no, I'm talking about experimental groups, so this is coming from Debygin group, and there is a group in Paris that is doing experiments, and they are measuring some, I don't remember now, some, yeah, essentially from equation of state. Yes, yes, they are, and they claim they don't see it. So this is, there are still there's still a debate whether this pseudo gap exists. And meanwhile, we calculate some other quantities which also have are associated with, are related to the pseudo gap. So, for example, spin susceptibility. Spin susceptibility, here you see as a function of temperature. And again, spin susceptibility, if the system, if there are pairs that are formed, the spin susceptibility should be should decrease. So, and we indeed see, so these are the Monte Carlo results for 3 lattices. So these are 3 different colors of dots. And the critical temperature is here. And we see the spin susceptibility goes down above the critical temperature, which supports the fact that there are preformed pairs in the system. And actually, very nicely, it turns out that there is one experimental point. Is the Ketterle group measured the spin susceptibility, and actually it nicely coincides with our results. So again, this supports the pseudo gap. Also, another thing, the so-called spin drag. So the spin drag tells you can calculate the yeah, spin drag is essentially the inverse of the spin conductivity. So it tells you how difficult it is to drag spin up against spin downs. So again, if the pairs are formed, that spin drag should increase. And again, you see that the spin drag raises above the critical temperature. So it tells you that our Monte Carlo results, whether they are true or not, they are at least consistent. So so using various methods, we get essentially the same. We arrive at the same conclusions. Okay, so diffusion, or maybe I will not talk about diffusion. So so I think I will finish at the pseudo gap. So I will not cover the viscosity, but hopefully Gabriel will come in a week or 2, and he will, because he is the main person who actually did the performed the calculation for the viscosity for the unitary Fermi gas, which is kind of very interesting quantity. So in a week or 2, he can explain some details, how these calculations have been performed, how these calculations have been performed, and this is the theoretical status of various approaches, and whether they predict pseudo gap or not. So we do dynamic mean field also, self-consistent T matrix. No, there's one paper and they claim they do not see it. And the non-self-consistent T matrix, they also see the gap, although much larger than our gap. So actually, we think they overestimate the size of the pairing gap. Okay.
2 T matrix calculations, are they by different groups or the same?
2 different groups. 2 different groups. This is the Italian groups.
So presumably the self-consistent people could also do a non-self-consistent calculation.
Yeah, I guess so. But there's only one paper on this. This is so yeah, I'm trying to recall what are the names behind this.
It doesn't matter, but
yeah.
You know, presumably they could check the other results.
Yeah, they could. They could. These people are producing many results with also with collaboration with experimental groups. So they produced a lot of results concerning unitary Fermi gas. So this is the main person there is Strinati. So So this is the status of the of our Monte Carlo calculations. So thank you.